Okay, so as you can see, my machine just crashed, so we're going to start without it. Can you hear me at the back? Okay, so anyhow, I wanted to say two things. One is projects. The projects are due, the project proposals are due this Thursday. There was a message in Piazza that clarifies this, and the web page is updated to clarify this. Someone asked a question with respect to some ambiguity on the date. I think it's correct everywhere. Maybe there was some old lecture note, but I think that it's correct now. Basically, up to 2 pages. As I said before, with a specific title. Please use this specific title because there's many of you that are sending messages. It's going to disappear either in my junk folder or among the many other things in my inbox. If it has this subject line, it's going to be easy to track and place in the right place. Questions on the projects? Okay, excellent. So a lot of you ask questions about, can I do this with a team of 2? Can I do this or that? In most cases, I think my answer was positive. So just figure out what you want to do. Hopefully it will be interesting. The current problem set. Questions, problems? Yeah.
I guess we all got very high accuracy in the bonus fraction without modifying the original perception algorithm.
I just responded to it on Piazza. So what's your conclusion then?
Probably we want to change the test data by using balanced test data instead of chain of the balanced chaining data, so that the classifier will be more biased to the majority of positive or negative. Biased classifier should expect to behave very bad in the real world example, in which cases the positive and negative examples should be balanced.
Well, you cannot change the test data. The test data is given to you, right?
Yes, we cannot change the test data, but no, I mean, want to do the bonus question here.
You learn something, and I think you will learn something. Now, I didn't tell you that what you will see will be very bad. Basically, I think there's one simple conclusion, without doing anything beyond what you've done, that perceptron is actually pretty good. Right? It learns well also on this. Now, you could try a few things, and if you're lucky in some configurations, you will get improvements. One suggestion I made, and again, I'm not guaranteeing that it will be easy to get improvement. All I'm saying is that it's interesting to play with it. You can look at the results that you get on positive versus negative separately, and you'll see something interesting as a function of how much training you do. But overall, I agree that perceptron, the simple perceptron, is pretty good. So the goal of this, not to say it's bad, is to illustrate that it's actually pretty good, and you can do some other things in order to understand better what's happening. Yeah.
No, I feel like it would be bad if you give me a balanced test data set.
If you train it on a different, that's true. If you train it on a different distribution than you test it, yeah. You can do the other direction also. You can train it on balanced and then give it imbalanced. Now, in this specific case, try this. I mean, this would be interesting. Depending on how much training you do and how easy the concept is, the function that you're learning, you may be surprised that you'll see pretty good results. Why is that? Any idea why I still expect that you will get good results?
Under what condition?
Even the conditions that you said, I'm training on balanced and then I'm testing on unbalanced or vice versa. Yeah? So what is the function that we ask you to learn, that we generate the data according to? Well, what's special about this function?
The errors you made.
I'm looking for two words. This function is linearly separable, right? So it's linearly separable. You have a pretty good algorithm. It's going to find a good separator. Now, is the separator going to be perfect or not? I don't know. That depends on a couple of things. One thing that it depends on, even when it's linearly separable, it could be linearly separable and it could be linearly separable, right? What about the function that you are learning here? Is it easy, hard? We explain how we generated the data, so think a little bit about it. What we explained is how we generate negative examples and how we generate positive examples. We gave you MATLAB code for it. Notice that, I can't remember exactly the details, but we told you how many on bits. So it's L out of M out of N. N is fixed for now. M, let's say it's fixed now. And then L determines whether it's going to be a positive example or not, right? So let's assume L is 10, which means that to be a positive example, you have to have more than 10 on bits. To be a negative example, you have to have less than 10 bits. Now, the difficulty of this function is determined by how we generate the data, right? We can generate, I don't remember if equal counts to which side, but let's assume I generate 9 and 11. That's one option. I can generate 2 and 25, right? 25 on bits for positive example, 2 bits for a negative example, and many other options. So this will dictate how easy your learning task is, really. So if the learning task is very, very hard and you don't train it enough, then you will see problems when you change the distribution. If the problem is easy and you train it enough, these two are dependent variables, doesn't matter what you do. It's going to learn it well. So basically, this is the playground that you have for this problem set, and we wanted you to understand this. And from what I see on Piazza, a lot of you are already running experiments and getting results and so on. So hopefully you see differences. And we gave you a bunch of experiments that hopefully will show enough differences and allow you to understand what's happening. It's a playground. You can do other things, right? You can change the way we generated the data, and you'll see that it impacts the result that you see. So there's many things you could do that we didn't ask you to do because I think you have enough. But anyhow, this is just to answer the question. So I didn't expect you to see bad behaviors. In fact, we expected you to see good behavior, but you can still play a little bit more. You can change the imbalance, for example, different ways and see what happens. Other questions? Okay, so let's start. So I already said that. Just to remind you, I mean, projects are due. This is what I hope you'll send. Okay, so where were we? So last time we talked about PEC learnability. Just to remind you, we basically gave a simple condition under the consistent learner thing. We basically said, here is how to make sure that your PEC learnable, that your concept class is PEC learnable. You take a sample, you find some hypothesis that is consistent with all the sample, and then we proved that for large enough M, if you're consistent with the sample, it's going to be good. The future is going to be good. That's basically what we showed. How large should the sample be? This is really what you have to take care of, right? So we show that M depends this way in the size of your hypothesis class and your complexity parameter epsilon and delta, and you want to make sure that this is still polynomial. If it's still polynomial, you're PEC learnable. If not, you're not PEC learnable. As simple as that. In addition, we had another condition on efficiently PEC learnable. Can you compute H efficiently? So that's actually a very, very simple thing. And then we went through a lot of examples. I'm not going to go over the examples, just run through this. So we basically gave a lot of function classes that we basically said, M is not too large for them because we can count, take the log, and see that we get polynomials. And then we talked also about, so this was a summary slide for different hypothesis classes. We also talked about the interesting case of two-term DNF, where we said, size-wise, it's okay, but it's not efficiently PEC learnable because we don't know how to find a good hypothesis. And then we changed the representation, and we found that it's okay. So basically, this was, again, an important lesson in the importance of representation. So, and then I gave very quickly a few interesting results that, again, if people are interested in kind of complexity and so on, they can go and look at the details. I want to mention one thing here, for example, for deterministic finite automata. Deterministic finite automata are not learnable in the standard model. So basically, if you get as input examples, which means you get examples, or let's think about context-free grammars, or let's stick with finite automata. If you take examples which are in the language, positive example, outside the language, negative examples, you cannot PEC learn the automata. What can be shown, and this is very interesting, is that you can change the learning protocol, and instead of taking random examples of positive and negative, you change it to a learning by query. Basically, you as the learner proposes examples and asks the teacher, is this a positive example or a negative example? Under this protocol, you can actually learn the finite automata. So this is one classical example where the type of learning protocol actually changes the boundaries of learnability. And again, if people, I think I put a pointer to this paper. If people are interested, there's been more work on understanding these kind of issues. Okay, this is where we ended. So as we talked about PEC learnability, there were two concerns that you raised. One of them is this consistent learner hypothesis. Why do you insist that your learner will take this training data and find a hypothesis that is completely consistent with it before you can say that it's going to be good in the future? And it was easy to make this assumption because the proof, the Occam's razor proof, was very simple. But in fact, it's not a necessary assumption. We can do what is called agnostic learning. So we assume that actually there is no hypothesis in capital H that is consistent with the data. Nevertheless, we can say something. In this case, the best we can hope for is that we'll achieve a small training error. It will not be zero training error. That's the training error, right? The number of examples on which F is different than H, or H is different than whatever Y is supplied with the training data. And we want to guarantee that this hypothesis will be good in the future. That's what we care about at the end. So in this case, the technical tools are a little bit harder. One has to use what is called hefting bound. It's a version of Chernoff bounds, if people are familiar with that, that basically say that if you care about, if you want the true probability is P, if you estimate it with P hat, the probability the difference between them is greater than epsilon goes exponentially fast down, exponentially in epsilon and in the number of samples that were used to estimate this P hat. So again, think about a coin tossing. P is the true bias of the coin, and you just toss the coin 100 times, M is 100, and you get some estimate to the bias. This estimate is P hat. And the difference between the true bias and the estimate goes exponentially fast down. So once we do this, we can actually have the following bound. Basically, the game that we're playing here is there is some hypothesis that has this error. This is the true error of the hypothesis. Now, we are using this hypothesis, and we're predicting on the data that we see, on the sample data. And on this sample data, we get some training error, right? If we do it many times, M is large enough, then the gap between these two is going to be small enough, and this is how we quantify it. Again, just like before, this is for a given H. The probability, we want to bound the probability that there exists some H in our hypothesis class that has bound that is greater than epsilon, and we want this quantity to be as small as we want, as delta to be small. Just the same game as before. We are trying to isolate either M, or we're trying to write this in a better way. So here is one way to write it. The real error is going to be smaller than what we see on training, plus something. And this something makes sense, I hope, right? So what does this something says? It says that this something is going to go down as M grows, which makes a lot of sense, right? I hope. Larger M, this gap goes down. It's going to go up with the size of the hypothesis, right? So if you have a very, very large hypothesis class, then it's going to be very easy to get here something small, right? But you're going to pay a penalty here. And of course, it's going to go down also as a function of 1 over delta. Yeah?
What if delta is H times the...
Oh, minus, sorry. Should be a minus there. Yeah. It's the same thing that is here. Yeah. Okay. Okay. Okay, so this is one way to write it, as the gap between the error that we care about and what we observe. And I can also do the same thing, just doing some algebra, and I can isolate M out of this. And I'll tell you how many examples do you need to see in order to make sure that your error isn't going to be too much larger than what you've observed in the training. And basically, that's what we say. We say, just to state it, an agnostic learner, we call it agnostic because it doesn't care where the target function is coming from, right? You see data, you don't care where it's coming from, and you're going to learn into H. So if an agnostic learner which makes no commitment of whether F is in H, and return the hypothesis with the least training error over at least the following number of examples M, can guarantee with probability at least 1 minus delta that its training error is not off by more than epsilon from the true error. That's what we want, right? And this is M. And again, M makes sense. It depends on the log of the size of H, 1 over delta, 1 over epsilon. Okay, so basically so far we addressed one of the concerns. It doesn't have to be consistent. We can just attempt to minimize the error. But the basic thing that we've seen is that the learnability of a concept class, or the learnability in general, depends on the log of the size of the hypothesis space. And this addresses the second concern that you had. This is, I mean, all this theory is true for finite hypothesis classes, because we're talking about the size of H. So what we want to do today is we want to generalize it. And a simple example would be rectangles, real valued plane. And I want to learn a rectangle in the space. That is, my concept class is defined by 2 numbers or by 4 numbers that define a rectangle. And I'm going to give you positive example and negative examples. And you gave me an algorithm. The algorithm that you suggested last time is look at the positive examples and do what? Find the lowest x value, the highest x value, the lowest y value, the lowest y value, the highest y value of the positive examples, and form a rectangle. So this way here are more positive example, this is it, and so on. And this makes sense, right? If I told you that the data is going to be consistent with the rectangle, you know that you're going to do okay. And the question is, can you prove that you'll do okay, and can you say something about how many examples do you need to see so that the future will be good? And currently we cannot, because we don't have a good theory for it. So we want to be able to generalize the theory to the case of infinite dimensional spaces. And the intuition is that even when we talk about infinite dimensional spaces, we can have hypothesis spaces that are more expressive than others. Right? So we talked about rectangles, but we can talk about 17-side or up to 17-size convex polygons. It's a much larger class. Or we can talk just about convex polygons, much larger class. And we talked about linear threshold functions, but we can talk about conjunctions of linear threshold functions, right? So instead of 1 separator, I can say, well, I have 2 separators. And my class could be defined as positive example are those that are made positive by this and made positive by this. It's a more expressive class of functions. And of course, you can increase the dimensionality. You can talk about polynomial or multinomials of degree 7. So we need a measure of expressiveness of an infinite hypothesis space, and we're going to define what is called the VC dimension, called after Vapnik, Chervonenkis, 2 Russian mathematicians that invented this. And it turns out that this provides a good measure and in fact replaces the size of H, or the log of the size of H. So what is it? So in order to think about it, we define a notion of shattering that basically has to do with give me a point set. When you're given a point set, you can label it in many, many ways, right? You can say all of them are positive, all of them are negative. These are positive, the rest are negative, and so on. And if you can split a data set, a given data set, in many, many different ways using your function class, it means that you have a pretty expressive function class. If you cannot do it, you don't have an efficient. an expressive function class. So that's what we want to define today. So let's start with 2 points, right? So here is a set of 2 points. And for 2 points, I can split them to positive and negative in 4 ways. I show 2 of them here. One orange and one red. The other one is orange, the other one is red. And I also could show 2 other ways, both red, both orange. And these 2 points in the plane, I can separate them with a linear separator, as I show here. The other 2 configurations I can also separate with a linear separator. But, so linear functions in this example are expressive enough to shatter 2 points. Now, here's another set of points, much larger. So this configuration, these are red and these are orange, I can separate with a linear function. But this configuration, other are red and some are red and some are orange, I cannot do with a linear function. I can try several times, not going to work with a linear function. But with this class of functions, I can separate it. Right? So this is the intuition that we have here. Linear functions are not expressive enough to shatter these 13 points, or 13 points in general. But this class of blue curves can do it. So the class of blue curves is a lot more expressive than the class of linear separators. So let's make a theory. Let's formalize it. So we're going to say that a set S of examples is shattered by a set of functions, H, capital H, if for every partition of the examples in S into positive and negative examples, you can find some function in capital H that gives exactly these labels to the examples. Okay? So let's look at the quantifier. So we have a set of examples, a fixed set S, and we shatter a set of examples, not one example, we shatter a set of examples. We shatter it not with one function, we shatter it with a class of function, capital H. Okay? And we shatter it if all the possible dichotomies of this S can be expressed using functions in H. So let's take some examples. So here is my first class of functions. These are left-bounded intervals on the real axis. So it's a function of A. And here is how the function class is defined. It's a function class parameterized by A. All the points between 0 and A are positive. All the points larger than A are negative. Okay? So it's an infinite class of functions, right? And let's see. So if I have 1 point, my set S is of size 1, which means it's a real valued number, a positive real value number, because this is the domain of the function. Can I shatter it? I can shatter it. If you give me the number 5, I'm going to choose, and you tell me, you know, I want this to be a positive example. I'm going to choose A to be 7. If you want the number 5 to be negative, I'm going to choose A to be 4. Right? Any point that you give me, and any choice of how to label it, I can find a member in this class of function that will do it. Agreed? What about 2 points? Now you're giving me 2 points. Let's say 5 and 10. Can I shatter it with this class of functions? Why not? So if I have 5 and 10, I can make both of them positive. I can make both of them negative by placing the A below both of them. And I can make the lower one positive and the higher one negative by placing the A between them. But I cannot make the 5 be a negative example and the 10 be a positive example. So this class of function is not expressive enough to give me all the options I need for 2 points. Okay? So this is what we said. Here is a set of 2 points. This is a point and this is a point. And this is a configuration, negative to the left of the positive, that I cannot shatter with this class of functions. Clear? Okay. Let's go to a more expressive class of functions. Now I have a class of functions, still infinite class of functions, parameterized by two numbers, a and b. So it's intervals on the real axis. A, b. B is greater than a. So let's think about 2 points here. Can you shatter 2 points? What about 3 points? So how many configurations are there for labeling 3 points? 8 configurations, right? Because each one can be either positive or negative. So I have 8 options to label it. All 8 configuration I need to check, and for each configuration I need to find, so let's say I gave you 3 points, 1, 2, and 3 on the real axis, and there are 8 possible labelings of them, and for each configuration out of these 8 possible labelings, you need to give me a function in this class. That is, you need to give me a and b. Can you give me a and b for each of the 8 configurations? No, I see no's. Give me a function, give me a configuration that you cannot shatter. Plus, minus, plus. So if you give me 1, 2, 3, these are the points, and you want the middle one to be negative and the other two to be positive, this class of function cannot do it. Agreed? Okay, so, this is just a clarification. We want to make sure that we know that this is a class of functions, right? There are infinite functions here, parameterized by these two numbers, a and b. And this is the example, right? So I took 3 points. This should have been a. And if I want to label them plus, minus, plus, there's no function in this function class that can do it. Okay, so all sets of 1 or 2 points can be shattered. But, in fact, no set of 3 points can be shattered. Agreed? Okay, let's take another example. Half spaces in the plane. Half spaces, another way of saying linear functions in the plane, hyperplanes. So let's think about this here. So how about 2 points? I give you 2 points. 2 points mean 4 configurations. Can you always find a hyperplane that will do the right thing? Everyone is convinced? 3 points. Can you always find a hyperplane that will do the right thing? Now you have to consider 8 possible configurations. Can you always do it? Who says yes? Who says no? Okay, there was a question here. Okay, excellent. So here is an example of 3 points. They will all be on the line. And then you argue that not all 8 configurations of labeling them will be shattered. Why? Yeah, give me the labeling that will not work. Plus, minus, plus, right, will not work. If all of them are plus, then you can do it, right? But the interesting thing, if they're all on the line, on one line, I don't care which line, and the middle one is labeled differently than the other two, a linear separator will not do it, right? So not all configurations of 3 points can do it. But is there a configuration of 3 points that you can shatter? Just if you take 3 points in a general position, but general position means they're not on one line, then you can shatter it. Convinced? Okay, so sets of 1, 2, or 3 points can be shattered. Now notice that to be shattered, I don't need that all sets of 3 points will be shattered. I need that there is a set of 3 points. So it's true that not all, because you gave me an example, but we also are convinced that there is a set of 3 points that is okay. So sets of 1, 2, and 3 points can be shattered. What about 4? Who says no? You should vote. It's almost November. So who says yes? No one says yes. Okay. So why is it that the answer is no? So if they are all on the same line for the same reason as in 3, we cannot. But what I want to know, is there a set of 4 points that you can shatter? Okay, so now it's more interesting because I have yeses and no's. So who says no? Okay, so which means that you think that no set of 4 points can be shattered. Why is that? It's? Right, so first of all, it's difficult because we have to consider how many configurations? 16 configurations. So let's see how we can do it. So we can, one thing is we can enumerate it, but we really have to be systematic here. So let's take some interesting configuration. Let's assume that they are all on a line. If they are all on a line, you are convinced that we cannot do it. If 3 are on a line, also we cannot do it for the same reason as before. Okay? So now we can say, okay, so no 3 are on a line. This is our general configuration. So now we have 4 points in general configuration. Can they be shattered? Why not? Any general argument for why is it that 4 points cannot be shattered? Okay, that's true. More concise suggestion, yeah.
Well, I didn't really hear what it said, but I mean, basically, these two are positive.
Right. Yeah. So it's the same argument. So first of all, the claim we're making is that no set of 4 points, and really the quantifiers here are important. So I'm emphasizing the quantifier. So for 3, I said it can be shattered just because we found one set that we could shatter. Here I'm arguing no set of 4 can be shattered, and the argument is so we already addressed the issue of all of them are on the line or 3 of them are on the line. Other than that, I'm claiming that we can think about these 4 points as forming a convex polygon. So now, if one point is inside the convex polygon that the other 3 are forming, then I'm going to label it differently than the other 3, and I cannot shatter it. Otherwise, it's going to be on the line. Right? Think about the triangle, and then I'll have 3 points on the line, which we agreed is okay. So basically, this is the general situation, that I can take a convex polygon out of 3, and a 4th one will be inside it. Otherwise, there will be 3 on the line. And with the convex polygon, hopefully that's convincing. So no set of 4 points can be shattered. Okay, so that leads us, so we understand what the notion of shattering, and now we can define VC dimension. So before we get to the definition, I just want to make sure that we have the right intuition here. So by unbiased hypothesis space, I mean all the functions, right? So of course, if I have all the functions, I can shatter any set, right? Now, if I can shatter a very large set of X, it means that my function class has a lot of members in it. It's an expressive class of functions, or is less biased. And this leads to what I want to define. So I'm going to use VC dimension to measure this expressivity. It's basically going to be the size of the largest finite subset of X that is shattered by H. And it's important, again, the quantifier. Even if one subset of this size does it, it's already fine. So this is how we define it. If there exists a subset of size D that is shattered, then VC dimension is at least D. If no subset of size D can be shattered, then VC dimension is strictly less than D. So let's go back to the examples that we had before. We looked at half intervals as a class of functions, and I'm claiming that the VC dimension of half intervals is 1, because we could shatter 1 point, but no set of 2 points could be shattered. VC dimension of the intervals, AB, is 2, because no subsets of 3 could be shattered. Right? You gave me a set of 3 points, and I showed you that if the middle one is labeled negative and the other 2 positive, you won't shatter. So no set of 3 points can be shattered. Half spaces, the VC dimension in the plane, the VC dimension is 3, because no subset of size 4 can be shattered. Now, this actually shows that the VC dimension is less than 4. Right? Because no subset of size 4 can be shattered. Why is it 3? It's 3 because we found one set of 3 points that can be shattered. We don't need that all of them will be. We found one set of 3 points, and that already says that it's at least 3 because of this part of the definition. Okay, so again, some are shattered, some are not, but we don't care. We have one that is shattered of size 3, and the VC dimension is at least 3. Okay, so that seems hopefully intuitively like the right thing to do, because it gives us some idea of the expressivity of an infinite class of functions. Yeah. Vapnik, Chervonenkis, 2 people. And the dimension is after them. Okay, so why is it important? Yeah.
But if we really, like,
Yeah. In fact, very good question. So given a hypothesis class, it's actually intractable to compute what's the VC dimension of this, even though we could do it here, right? So, yeah, in principle, as a complexity theoretic problem, the problem of computing the VC dimension of H is intractable. But really, in most cases, we don't want to compute it. What we want is to understand what does learning depend on. And we now understand what does, in the next slide, we'll understand what learning depends on, and this will be good. We will never have, well, except for homework problems and stuff like that, in real life, you will never have to compute it. You will often have to bound it and argue this is the good hypothesis class because its VC dimension is better than this. And we'll actually, hopefully, at the end of today, we'll get to some interesting cases like this. So we mostly care about, is this larger than this? Or is this polynomial? More than exactly computing it. Okay, so why is it important? Intuitively, hopefully, it makes sense. It measures the expressivity of the class of function, but really it makes sense because of this. Because using VC of a hypothesis class H can completely replace the log of the size of H in the finite classes. So we can prove an Occam algorithm, just like what we had before, but this time for infinite hypothesis spaces. And it's going to go like this. Given a sample D of size M, we need to find some H that is consistent. I'm going to the extreme case of consistent hypothesis with all M examples. And if M is at least this, it's going to be good. What do I mean by going to be good? It means that with high probability, at least 1 minus delta, H is error less than epsilon. Basically, if M is polynomial, this algorithm that found the consistent hypothesis is a Peck learning algorithm. Okay? And notice that it depends on the right thing. Again, it's inversely proportional to epsilon. It's inversely proportional to log delta. And it is linear with the VC dimension. You know, the other numbers, you know, they don't matter. They've been changed. They're changing, you know, from time to time because people develop a slightly better technique. But conceptually, it depends on the right things. So it doesn't matter if it is 13 here or goes down to 7. It's still the same thing. Okay, so just as a sanity check, we prove this, and this is really the more general statement than what we've had earlier, because this is for any H, right? Could be finite, could be infinite, because VC dimension is defined also for finite hypothesis classes. Right? I didn't say anything in the definition that H has to be infinite. So just as a sanity check, what happens if H is finite? Can you say something about the VC dimension of H? What? No, but I want to, before we had something that had log size of H. Now I have something that is that says VC of H. And I want to just make sure that if H is finite, we are in the same ballpark, right? We did not invent something that is completely different than what we had at the beginning of today. So let's assume that you have a finite hypothesis class, okay? And that you can shatter a set of M examples with this finite one, okay? If you can shatter the set of M examples, you know that the VC is at least M, right? That's the definition. I can shatter with my H this set of M examples, the VC is at least H. What can you say? But now I tell you H is finite. Can you tell me something about the size of H? Yeah? Why?
Because if you dependence
Right. So here is a very nice argument here. So I have M examples and I can shatter them. So on one hand, we know that the VC is at least M. I'm using M examples, right? We know by definition of VC, M examples are shattered, VC is greater than M. On the other hand, if I tell you that H is finite and it can shatter M examples, how many different ways are there to label these M examples? 2 to the M. So I have to have at least one function for each possible dichotomy, right? So I have at least 2 to the M functions. So VC, 2 to the M, so the log of the size of H is VC. So this is the argument. In order to shatter M examples, I must have H that is larger than 2 to the M. And therefore, the log of H is at least the VC dimension. Right? So this is just a sanity check for us to make sure that we didn't invent a new creature that is completely different than what we had earlier today. Okay? So now that we have that, we can go back to the problem of learning rectangles and see is it pack learnable, the algorithm that we had before? And again, what do we need for pack learnability? We need these two conditions. We need VC dimension to take care of the sample complexity, and we will need an efficient algorithm. Okay, so first of all, for VC dimension, let's figure out what's the VC dimension of rectangles in the plane. So I'm claiming that some 4 instances can be shattered. Here are 4 examples, and I'm claiming that you can shatter them. Now, it's not true, again, that all 4 examples can be shattered. Agreed? Again, if you take all 4 on the line, can it be shattered? Why not? You need to give me a labeling. Plus, minus, on the line, you cannot shatter with a rectangle, right? You cannot place a rectangle anyway so that the positive will be inside it and the negative will be outside it, right? So, but there are some 4 points, and these are general position 4 points. You need to invent 16 different rectangles, right? You have to have a rectangle that leaves all of them outside. It's going to be here. You have to have a rectangle that leaves all of them inside. For each singleton, you have to have a rectangle that puts it inside, and all the 3 are outside. For every set of 2, you have to have a rectangle that leaves them inside and the other 2 outside, and so on. 16 options. But you can see that this works. What about 5? So this basically already shows that the VC is at least 4. Okay, so this is just the argument that some can and some cannot. What about 5? So I argue that no 5 points can be shattered. And the argument is very similar to what we had before, yeah?
So I don't understand why you...
Okay, so my argument is very similar to the convex hull that we had before. Basically, I'm going to say I have 5 points. There are at most 4 distinct extreme points. When by extreme points, I mean smallest or largest along y-axis and along x-axis. Now, it could be that I get equalities. That's fine. But there are at most 4. And then what I'm saying that I'm going to put all of them as positive and the 5th one as negative. And this cannot be shattered. Okay? Now, equality doesn't bother me here, because equality might mean that I'm going to have 2 points on one side. But that's fine. One of them is going to be negative, one positive, or I'm going to require that one positive and one negative, and this cannot happen. Question? Okay, so it's really the same argument from before, and as you said, you know, it's a hard problem, right? It's not always easy to come up with a good argument for why the VC dimension is this or that, but you know, it's a good exercise, at least to understand where are the boundaries. We know from here that it's at least 4. We know from here, I hope that, okay, that it's exactly 4. So that solves half the pack learnability question, because in terms of sample complexity, we are fine. VC dimension is small. Now we have to come up with a polynomial algorithm, but you already gave me an efficient algorithm, right? The efficient algorithm basically says, find the smallest rectangle that contains the positive examples. Because I promised you that there exists a rectangle, you know that if you find the smallest one, it will not contain any negatives, right? And then you get a consistent hypothesis, and it's a very simple algorithm, right? So basically scales linearly with the number of points. So we proved that axis parallel rectangles are efficiently pack learnable. By the way, is this going to be your algorithm in practice if you going to learn axis parallel rectangles? Or do you have a better practical algorithm? Find extreme points. It's basically the same, no? Finding the smallest. So the suggestion is to find extreme positive points. But I think that finding the smallest rectangles that contain the positive examples is the same as finding the extreme positive examples. It will return exactly the same rectangle. But the question I'm asking really is, yeah?
So instead of just finding the one that barely
I think this will be the best practical algorithm, right? So find the smallest that contains the positive, find the largest that does not contain negative, so right, sort of increase it on all four sides until you reach a negative example. So, and then what you want is to find something in the middle. And the reason is because, you know, the same intuition that when we talked about linear separability, we want a thick linear separator, right? Because we know that in the future, when people will sample points from this, they will not necessarily stick to the blue points inside and the red points outside. You know, there's going to be some noise. If we are somewhere in the middle, maybe we're better situated to handle this. And in fact, even today, hopefully we'll get to use VC dimensions arguments to explain why this actually makes sense. But for now, it's enough for us because this is spec learnable. We proved that it's spec learnable. Okay, so basically, you know, this is kind of almost everything we wanted to say in order to understand spec learnability. Now, what? Yeah, question. Okay, no. Okay, good question. So the theorem that I phrased is take your data, find H in capital H that is consistent with the data, and everything is going to be good. In exactly the same way, when I said it for finite classes, the same agnostic theorem applies also for infinite classes. I don't have to be consistent, and I can show that the gap between true error and training error is going to be small as a function of VC dimension. Okay. So the issue of consistency here is basically only. So we have to distinguish between algorithms and the theory that we developed. The definition of VC dimension is there only so that we will have some way to distinguish expressive hypothesis classes from less expressive hypothesis classes. Okay? So this hypothesis class is more expressive than this because its VC dimension is higher. And when I'm defining this, I'm defining it using a notion of shattering that has to do with consistency. Is there a function in this function class that has this property, or whether there isn't a function in this function class that has this property? You could try to refine this definition and say, is there a function in this function class that is almost consistent? It will not give you a better definition of expressivity of class of functions. Right? So this is what we care about. We care about a definition of expressivity. Just like in finite cases, you have size. Here we have a new notion of size. That's it. So once we establish that, and we have a notion of size for infinite classes of functions, we go to the learning. And the important thing here is this. right? So here it says, if you see this many examples, and the number of examples that you need to see is a function of the size of your hypothesis, or the VC of your hypothesis, then we are guaranteed with this Occam's razor theorem that the generalization error is going to be good. And here, the theory that we have for whether when you learn, you're completely consistent with the training data, or when you learn, you just minimize the error, but you don't get to zero, is exactly the same thing, irrespective of whether the hypothesis class is finite or infinite. Okay? So these are kind of two distinct things. In one case, it's just a tool to define size where it's infinite. We need a new tool. And the other one is how we use it, and basically we use it in exactly the same way, irrespective of which is h. We just want to minimize the error. Okay, so I wanted to say one thing, because all these bounds, what's happening here? All these bounds that we proved, and perhaps the nicer bound is the one that I had before. In the agnostic case, the one that looks at it as the gap between the error that you observe experimentally and the error that you will see in the future. This is the experimental error on the training data. This is what you'll see in the future, is bounded by this. And as I said, you can just now replace this log of h by VC of h. Everything is fine. This gap, this is an upper bound. Basically, it says, what's happening here? Okay. If you see at least this many examples, it's going to be okay. It does not say you must see these many examples, right? It's not, there's no lower bound that we gave. You see the difference? We says, if you see this many examples, everything is going to be okay. Do you have to see this many? Maybe you'll just see 17 examples and everything is going to be fine. So we need also a lower bound in order to do it. And I'm not going to prove any lower bound, but I just want to say that there exists a lower bound, and the lower bound is not very different from the upper bound. I'm just stating it here. Okay. Okay. Oh, this is the upper bound that we gave. Okay, lower bound. So basically it says that you actually have to see at least these many examples to be sure that you'll generalize well. Now, you have to understand that lower bounds in general in complexity have to be taken with a grain of salt, because basically what it means that there is a bad case, right? So there is a collection of functions such that, and a distribution from which you sample examples, such that you actually have to see these many examples to generalize well. Right? This is a lower bound. Now, and it turns out that the lower bound and the upper bound are not so different. Really, there's only a factor of 1 over epsilon or log 1 over epsilon between them. The importance of this is basically just to tell us, even though we have an upper bound and that upper bound is rather strict, it could happen that you actually need about these many examples. Doesn't mean that every example, every case that you see will be like this, but it could happen. So again, if people are interested in this, they can look at it. So conclusions. Basically, what have we done so far? We basically provided a computational framework, a theoretical framework, that gives a pretty good way to think about effectiveness of learning algorithms. Basically, we talked about the notion of sample complexity. We showed that it depends on either the size of h or the VC of h. And we said if the sample complexity is tractable, then it's going to be okay. So if you manage to produce pretty good hypotheses on large enough data sets governed by this, then you're going to be fine. And really, this is the important thing, because this is the boundary between learnable and non-learnable. In addition, we talked about computational complexity, which is also an important thing. And again, we show that there are cases where even though sample complexity-wise it's okay, you just cannot compute a good hypothesis for some representations. And you'll have to change your representation if you really want to learn in this domain. The important thing about this framework is that it actually gives rise to a lot of good ways to think about learning. It's been generalized in many, many ways. And I really gave here the very basic treatment. You can do the same thing and think about learning with noisy data and prove things like, this class of functions is not learnable with this type of noise, or is learnable with this type of noise. You can talk about learning under specific distributions. You can say, here is a class of function that is not learnable in general, but is learnable if the data is sampled from this class of distributions. And you can talk about probabilistic representations. We talked about, functions, but functions could represent probability distribution. You can talk about neural network, finite automata. A lot of other models all can be studied and have been studied within these frameworks. And basically, they give insight to learning. So the final conclusion is, even though it's not necessarily tight, in the sense that you will not look at these bounds and say, oh, I have to see at least these many examples, otherwise I won't be able to learn. What it does give you, it gives you a good model selection idea. I want to choose these hypothesis classes more than these hypothesis classes based on theoretical grounds. And moreover, this way of thinking allows people to actually develop good algorithms. So we talked about Wino, that was really an algorithm that started with some theoretical analysis, was driven by theoretical analysis. Can we achieve these bounds? And we're going to talk about support vector machines and boosting that are algorithms that are directly driven by PEC learnability. Historically, boosting was really driven by a question about PEC learning, and I'm going to talk about it next time. Support vector machines came from a different direction, but were also driven by the same type of issues. So what are the issues? The issues are really have to do with VC dimensions. So far, we discussed VC dimension in the context of a fixed class of functions. It was the class of linear separators, rectangles, and so on. But we can also think about ways to parameterize class of functions in interesting ways and think about their VC dimensions. So let's run through this example. Let's look at the class of linear functions parameterized by their margin. Here's the example I have in mind. Which of these classifiers would be likely to generalize better? H1 or H2? You agree that it's H2, exactly the same consideration that we had before. And your intuition is based on the margin. But if we think about the standard VC theory that we just talked about, we know that the error, the true error, is bounded by the training error plus something that depends on the VC dimension. But in this case, the error of both hypotheses was 0. They were consistent with the data. And the VC dimensions of linear separators in the plane is 3. So there's nothing to distinguish them. How can I justify the fact, or your intuition, that H2 is better than H1? And the idea is going to be to think about the notion of margin. So I'm drawing here kind of the thickest linear separator that I can plug in between the positive and the negative examples. And I want to introduce the concept of margin that we've seen already, but let's make it formal. So the margin of a point with respect to a linear classifier, wx plus b, is the distance of xy from the hyperplane, wx plus b equals 0. This is another way of saying it. It's this number. For a set of points, I can talk about the minimal margin with respect to the set, where I'm taking minimum over all xi's of this thing. Now I'm going to define a new class of function. Instead of just talking about all linear separators in the plane, I'm going to define h gamma as the space of all linear classifiers that separate the training data with margin at least gamma. Okay, so now I have an infinitely many hypothesis classes. In fact, they are embedded one within the other. And they are parameterized by this gamma. And it turns out that one can show, and I'm not going to show it, that the VC dimension of H gamma, again, H gamma is the class of all linear separators that separate a given data set with margin gamma. So it's a data-dependent definition of my hypothesis space. And it can be shown that this is bounded by something that has to do with R squared over gamma squared. This is a number that you've seen before. Where have you seen it? Mistake bound of perceptron. So this really is something important, right? Of course, people that proved it for perceptron had no notion of VC dimension, didn't know about it. But it turns out that this is actually an important constant. It's bounded by this. So basically what I can do is I can plug it in to my bound here and say the true error is the empirical error plus something that depends on is R squared over gamma squared. And immediately here, you get the intuition that you had before, right? Now you say, okay, so when we consider H gamma, it gives us the idea that large margin is going to give us VC, small VC dimension. So basically, it almost gives us an algorithm. It tells us the goal is not just to find a hyperplane, but rather to find a hyperplane that maximizes the margin of this data set, because this is going to minimize the VC dimension, and therefore will generalize better. Okay? So this immediately gives an algorithm. It says, there's one more step that we're going to do a little bit later that says, not only you want to maximize the margin, there is a practical way to maximize the margin. If you make sure that the size of your W is small, it will result in maximizing the margin. So basically, there are two steps here. One that we did, we said we want to minimize VC dimension. To do it, we want to maximize the margin. That we understand. In a week or so, we're going to show this, that the practical way to maximize the margin is to find small w. So among all vectors that separate, all w that separate the data, we're going to try to find the one that has smallest size, and this will give us a new linear separator algorithm. A new member in the sort of class of algorithm that you're playing with in this data set. Okay, that's it for today, and we'll see you on Thursday.
Now we generalize the hypothesis space to be infinite. But the example space is still finite, right?